Well, now we mentioned in the last video that the angular quantum number um, is actually a description or a descriptor of the shape of the orbital. And we showed a plot that looked like this, where it said, where we said that the electron is most likely to be close to the center here and gets less and less likely to be in any position out here because the probability density is going down. So it becomes less likely out there. And now, this is an interesting phenomenon because this means that the shape of these that the electron of the cloud that the electron can be is basically just a sphere, okay? And so the 1s orbital, or 1s subshell, I should say. So the 1s subshell it is just a sphere that's around the nucleus. The 2s subshell is a sphere that surrounds the 1s subshell, and the 3s subshell is a sphere that surrounds the 2s and the 1s. So they're basically like eggs inside. You know those eggs where you take off an egg and then there's an egg inside it. You take off an egg and the eggs keep getting smaller and smaller. Well, that's kind of how the s orbitals are. And this is actually an indication of the probability of where an electron is. So as you get closer and closer to the nucleus, the electron it goes to an asymptote where it's more and more likely that the electron is found there. So this is distance from the nucleus, this r. This is the likelihood of finding an electron there. Okay, and so this is for the 1s. So as we go to the 2s here, we see that there's a big probability right here of finding an electron at this distance from the nucleus, but there's a 0 probability of finding an electron here, and then you have the same shape for the 1s that's shown here. So this is where the 2s electrons are, is in this region, and it gets lower and lower as we go out. And as we go to that third shell here, there's essentially two spaces where the probability is 0 that you will find an electron. These are shown by kind of these white markers up here. So an electron will never be found this distance from the nucleus and will never be found this distance from the nucleus, no matter what. Those are what are called nodes, or mathematical nodes. So these are the shape of the s orbitals, and this is the only one that's a sphere. Once we start getting to the angular quantum number starts becoming, greater than 0. So that's for angular quantum number of 0. This is for angular quantum number of 1, where the subshell actually has 3 orbitals. And an orbital, each orbital allows for 2 electrons to be put in it. So in this case, we can have 2 electrons in the 1s subshell. We can have 2 electrons in the 2s, well, the 1s orbital, so, and 2 electrons in the 2s orbital. So that's how it works. Once we start getting to orbitals here, p actually has 3, and these lobes, the shape of these orbitals, they look kind of like dumbbells, right? It's kind of like a dumbbell or 2 balloons tied together. And they're oriented in different ways. So these are overlapped, where you have this, imagine this being moved over to here and overlapping and being right here, okay? And this being moved over here and overlapping being like right there. And so that would be the shape of all of the orbitals in the L equal to 1 subshell, okay? You can actually fit 6 electrons into the p subshell, into a p subshell. Start moving to the D subshells. Now the D subshells, they get even kind of a more crazy shape, where they kind of look like the p ones, but they have 4 balloons tied together. Imagine 4 balloons tied together, and you got these lobes out here where the electrons reside. And these, again, all overlap, so you get one that's oriented this way, one that's oriented along the XY, one that's oriented in this plane right here, so it's around like this, and so on and so forth. And these are all overlapping, so these are all where the electrons are, and then the final one looks kind of like this with a little ring with one of those p orbitals stuck through the ring. Okay? And then once you start getting up to f orbitals, they just get incredibly complex. The shapes of these things are. So that's where the electrons are around the nucleus, based on the angular quantum number. Okay. So another way to represent these orbitals, instead of drawing those shapes, we essentially just draw these energy diagrams. And remember that the energy increases as you increase the principal quantum number here. This is the energy diagram for hydrogen for things with more than one electrons, which is pretty much all other atoms. The energy diagrams look something like this, where you have the principal, the first place you can put electrons, where the n is equal to 1. You'll only have one L that it can be, 0, which we represent as S. And then you put a little box where you put actually the electrons in. And the electrons look like half arrows. They look like half arrows with only one lobe, so you represent electrons like this right there. So they look like this. And if you want to put a pair of electrons, they look like that. All right? So that's what an orbital diagram is. Notice that the energy level is equal for the different L values. L equal to S, so L of 0 and L of 1 here. The energy level is equal for these two over here in the hydrogen. For non-hydrogen atoms, the energy level for the P is higher than the S. And so that's an interesting phenomenon. It has to do with repulsion of electrons and how they repel each other. Since electrons repel each other, however, you have to ask, well, how many electrons can you put in any one of these boxes? The answer is 2. You can actually put one pointing up and one pointing down, just like I showed you right here. Now the question is why, and that has to do with the magnetic spin quantum number, which will be the last quantum number we discuss.